all the presenters, everyone that attends this conference is so friendly, so willing to teach, so willing to learn from you too. So it's not just watching these videos, it's kind of getting that insight afterwards and around at dinner, at drinks, like all the other aspects of the conference besides just like that technical information.
Okay then, 1:15, so I think we should be ready to get started. My name is Conor Spilsbury. I work at Bloomberg and I work on a group of teams with high volume client-driven applications. As I've been in design discussions around these applications, it's not always been clear in these as to what our application actually needs to look like to handle the amount of work they need to go and do. It can become a bit of a puzzle at times and can take some discussion to actually work out. And so if we understand the foundations of concurrent design, we're all going to benefit from it. And we're all going to be able to use these tools much better. And so today I'm generally going to approach this as if we were working together back at the office with a whiteboard. And we're all just diagramming on it, standing around, discussing things. It means heavy on illustrations and diagrams, a little bit lighter on code. And so that does mean that this talk, it's not going to be a complete reference by any means. We're mostly going to focus on the behaviors of threads and coroutines here. But it's going to give you the jumping off points for when you encounter some of these in practice and you need to go and dig deeper. So that when you're faced with an application that's receiving thousands of simultaneous messages, or like an application that is constantly making external I/O or to get some data or just crunching that data, we're going to use that to go and look at how far can we actually take multi-threading. We'll then have a perspective shift and look at in which we'll go and lift scheduling out of the kernel and back up into our app itself. And what we need to do here and where coroutines are going to help us with this with cooperative multitasking. And we'll have understood that the type of work that our apps are trying to do matters, and how the shape of our problem is going to impact what we use between threads and coroutines. And taken together, this should all give you the intuition as to the behavior of the concurrency we'll see in our applications and how to adapt to the shape of our problem. So, let's say we are going and designing our application. We're standing around at the whiteboard, or we're already going and writing our code. Probably the first thing we're going to try, if we know that we're going to have to do a lot of work, is just throw threads at the problem. It's going to be what's most familiar with us, and we can go and create a thread per message. We have the number of threads on the x-axis here, and we can go and plot that as we increase the number of threads, our throughput to our task is going to just increase. Fantastic, easy, job done. High fives all round, call it a day there. But no, not so fast. We're engineers with thinking about scaling here. We need to see how far we can take this. Before this is something that we want to go and release to clients, we probably want to stress test this, see where those limits actually are. And of course, we're only a couple of minutes into the talk, so we're not just going to end here. So let's keep going. Let's just add more threads, keep going, see what actually happens. Cool, something happened. That throughput that was scaling so nicely hit this inflection point. And it's not just a plateau or diminishing returns at this point. It's actively getting worse. We're losing performance. So we can add thousands of threads and end up just being no better than if we were only to use a few threads. So let's think about this. Why is this something that we see? Well, let's start by going and looking at where our application's running. We're up here in user space. This is going to be a sandboxed environment. It's isolated from direct hardware access, and it's where our code can execute, but can't directly touch files, sockets, or physical memory. When our code needs to access any of these things, we have to go to the kernel. And that's the same when we create a stood thread in our code. There's a lot going on underneath that call itself. We're actually going and making a request to the operating system, which is going to create an OS thread for us that's going to be managed by the kernel itself. At this point, we need our threads to actually run somewhere. We need some hardware beneath it, CPUs, GPUs, whatever. If it was as simple as having an individual thread per CPU, then this would be easy. But in practice, we're always going to have more threads than hardware, CPUs, and hardware threads available to run. And that's why the kernel has a scheduler. It's responsible for taking those threads and getting them to run on our actual hardware. And it's great for making it look like lots of things can be running at the same time. Like we went many, many years with single core machines and still user interfaces trying to do a lot. It was doing a great job of multitasking. But this does break down when we have a lot to do. We've given the responsibility of scheduling to the scheduler, but we need to know when to take back that responsibility as well. And so at any point in time, these threads can be in one of these states. It can be actively running on the CPU itself. It can be runnable, just on a queue on the CPU waiting to be picked up and to be run. Or it can be blocked. It'll be in a wait queue somewhere. It'll be off the CPU itself, somewhere else, just waiting for the resource to become available. And it's the scheduler which is going and moving these threads between these states. It's deciding who runs, when, and for how long. And so there's a classic example of this within our application where we can create two threads in our application, one after another. Thread A, thread B. From our perspective, it looks serial, we're just creating them one after another. But as soon as we've created them, we've passed that responsibility over to the kernel, over to the scheduler. And that's going to decide which one is actually going to run, not just first, but also it's going to go and determine whether or not there should be any interleaving of execution. B could start first, it could stop, and then A could run, and then we could go back to B again. And that interleaving is something called context switching. And it comes in two forms. We have preemption, which is when the kernel is going to make these decisions for us based on, for example, time slicing. And then we have voluntary, which is where it's driven by our application and our decision to go and block on a resource. So taking these one at a time, let's start with preemption. Schedulers, such as like Linux's CFS, completely fair scheduler, they're trying to aim for some baseline fairness. It means that each thread is going to get some amount of time on the actual CPU itself. When the thread's time is up, the scheduler is going to perform a context switch. We're going to switch to another thread. And that context switch is going to go and store the state of that thread, any registers, any state associated with it, and then have to go and load the state of that next thread. This is concurrency. It's that interleaving of work. We start one thread, and then before it's complete, we switch to another, and vice versa. We've got threads being swapped in and out. This is where concurrency comes into our actual scheduling itself. And think about what will happen if the number of threads we have just explodes, like we were seeing on that diagram earlier. If every thread needs time to actually be running on the CPU, and there's going to be some sense of fairness to make sure that each one does get a bit of time, the more threads we have, the more context switching we're going to have and experience as each thread tries to get its own go on the CPU. Let's look at the second type, blocking on I/O. So imagine we have this function. It's called read. You don't need to know how it works or anything, but it's just trying to get data out of something, in this case, a file descriptor. When a thread calls a function like this, which blocks until that data is actually available, the scheduler is going to mark that thread as blocked. When it does get blocked, it's going to get taken off of the CPU itself, and it's going to be put over into a dedicated wait queue for that resource. Meanwhile, on your CPU it was originally on, something else entirely could be running. It could be a different thread, a different job. Eventually, when data is ready, the kernel is going to go and wake up our thread again. And so at that point, it's going to mark a thread runnable. It's going to add it back to a queue. And then at some point, that's going to be picked up on a CPU again. And note that it doesn't have to be the same CPU it was on before. It could be a different core. Now, if the data had been available immediately when we first tried to get it, then we'd just return immediately. The thread wouldn't block. We would just continue as we were. And this is really where that cost is really coming from. Like the operating system, it can only handle so many threads before context switching and that overhead starts to dominate. We're just wasting time creating, destroying threads for short-lived work. If every message was to get its own stood thread, we're going to spend just a considerable amount of time context switching instead of actually doing work. This is oversubscription. We're trying to do too much with too little. So what can we do to try and prevent oversubscription? Something to constrain the number of threads we create so that we don't go past that inflection point in our graph. Well, that's where we have thread pools. When many threads are becoming runnable together, and the kernel's deciding who runs where, and we start having threads competing for CPU time, we can start to fix that by limiting the number of threads we have at any point in time. Often fixed to one thread per logical CPU core, but can be more, and some thread pools even have a growth policy. We push work items into a queue, then workers in that thread pool are going to pick up that work and execute it on our cores. In this way, we can multiplex all of the work we want to do in our application, or the many tasks, onto a smaller number of OS threads. In doing this, it means that we're limiting the number of runnable threads at any point in time. And therefore, we can prevent oversubscription. We've moved from hundreds of threads competing to just n threads busy and then a queue of tasks behind them. But of course, we've still got the same amount of work to do, just fewer threads to do it on now. So we're going to be nowhere near the same level of throughput as we were before. But we've amortized the cost of threads by reusing them and bounded the number of threads to control the actual resource usage. But we've made it so that only n things can be in flight at any point in time. Because not only do we have a fixed set of threads running on a fixed number of cores, but we're now no longer getting the same amount of concurrency. We've bounded our concurrency here. Previously, we were having all of this interleaving going on. The scheduler is going into taking responsibility for that, making sure that each task got a fair amount of time to run. And this is critical, really. Like threads are great for providing parallelism up to the number of cores, and then we get some concurrency beyond that because the scheduler is going to preemptively start switching tasks in and out of those hardware threads. We've just seen the problem is that the scheduling starts to slow us down, and so the thread pool helps us stay below this, but at best, we're just going to hit that throughput peak depending on what values we set and prevent oversubscription. At worst, we're pessimizing the amount of work and the amount of concurrency we can actually achieve. Like our problem, it fundamentally requires us to scale beyond the inflection point size of a thread pool. And so we've lost something here. That smart part of preemption, that scheduling that the kernel was doing for us, that would let us have many more things in flight. We would start one job, it would switch out to another job when it was ready. Instead, in our thread pool, we have a couple of things in flight and then everything else in a queue behind them. And this is like really important. So I just want to take a moment just to get these definitions down. Parallelism, it's all about multiple tasks running at the exact same time. It tends to be a hardware thing. So they're going to be running at the same time on different cores. Concurrency, it's about multiple tasks in progress during the same time period, but not necessarily running at the same instant. And this is achieved by interleaving that execution, that time slicing we were saying. We can start one task while it's in flight. Before it's complete, you can switch over to and working on another task. So we solved our oversubscription problem with our thread pool, but now we have a concurrency problem. And up to this point, we've been delegating the responsibility of scheduling to the kernel scheduler because it is often good enough. We can get a very long way from it. But if we want to be able to go and handle more complex use cases and handle more volume perhaps, then we need to look at what we can do to take back more of that responsibility, bring it into our application and make our applications do what we need for the scheduling aspect. With a thread pool, we don't know when things are ready. We have to wait for things to complete before we can process the next message. So what else could we do to try and solve that? Event loops are one approach. This is the start of trying to lift that scheduling out from the kernel and into our user space, into our application. Instead of the OS managing threads, thousands of block threads or our thread pool, we can instead, in our application, again, multitask many tasks, but now just onto a single thread which is running in a loop. And you may have seen these in places where you need massive numbers of connections cheaply. Something like Node.js, Nginx, BoostAsio, they all do this. Because event loops, they're just a single loop in which we're waiting for something to happen and then dispatching that to something responsible for going and handling that. Once it's done, it returns to waiting. The goal here is that we're trying to do more work, but without the thread doing the scheduling for us. We want to take on more responsibility, as it could be cheaper if we do it ourselves than relying on the scheduler to do it for us. And so we end up with a queue of ready tasks in our event loop. Just a quick slide piece of code here, but we end up with, we've got a queue here, and we have some function running on a thread, which is just popping tasks from the front of it. And these are all small, non-blocking work. There's no waiting. But with the event loop, we're trying to get that feedback loop in place when we moved to a thread pool. Well, we started to lose, and we couldn't have more work in flight. We don't want to put something on a thread until it's actually ready to do some work. We need some way to indicate to the event loop that our task is ready. That is, if you go and take me off the queue, I'm ready to immediately continue. I'm ready to immediately go and run. Actually have something useful to do. So instead of blocking, we can go and, for example, ask the operating system, please tell me when this resource is ready to use. And readiness means that the operating system is guaranteeing that if we go and try an operation, like reading from a socket, it won't block. There's data waiting. As soon as we try and read it, it's going to be there. Like, remember our threading diagram from earlier as it went through the different stages and saw the thread get blocked? This is exactly what we're trying to avoid. We're trying to not have to pay that cost of waiting in our application. Instead, we're going to wait for something to tell us when is that socket ready and when can we start reading from it. And so the event loop is just a thread that is repeatedly asking the operating system, what is ready right now? Then it dispatches the corresponding callback to actually go and pass it to the handler. And then it goes back to just waiting for another event to happen. If you want to learn a little bit more about exactly how we can turn things from being non-blocking and readiness and all that, one of my teammates at Bloomberg, Philip Gelman, he gave a great talk at ACC a few years ago called What I Learned from Unix Sockets. Highly recommend it. But while non-blocking IO avoids idle blocking, we're now forced to express our program with callbacks and all of these handlers. We're no longer writing code in straight line logic anymore. We've got callbacks, things that the event loop is going to call later. And this is the trade-off we've taken with taking responsibility from the scheduler back into our application. We've been relying on the kernel to be smart enough to recognize what we were doing and yielding our threads in the past, but now that's something that we have to be doing. And that's why it's so important that what we're calling is non-blocking. Remember, this was one of the problems that we had with the thread pool. It removed the smartness as to when we started to bound our concurrency, and we no longer had that preempting. And so we still need something which we can go and get a signal back to our event loop and say, hey, I'm actually ready to go and schedule this because there's something useful that I can go and do. And that's something we're going to have to go and do ourselves now in our application. And that's where coroutines come in. They're going to let us write blocking-looking code without actually being non-blocking under the hood. So let's dive in. So what even is a coroutine? Well, the typical definition is it's a function that can suspend itself and then be resumed at a later point. So in C++, we can do this by co-awaiting something. This is going to yield until the underlying thing, say sync read in this case, is ready. There's some data to get out of it. At which point, when it's ready, we can then resume again and continue from where we left off. And let's remind ourselves of this diagram from earlier, where our application is actually running. We've seen how preemption can reduce our performance, and really any time we go from our application and cross this boundary into the kernel, it's an expensive system call. So the fewer of those, the better. We want it to be able to express everything up in user space. And so with coroutines looking a little bit like functions, let's start by going and looking at just how we call regular functions. When we do call a function, we get a stack frame. It's going to contain things like the parameters for that function, local variables, snapshot of any registers, return address, frame pointer. And the lifetime is tied to the stack frame itself. Once the function returns, the frame is plopped off the stack. It's gone. But C++ 20 coroutines, they're stackless. There's no separate dedicated stack like an ordinary function that we've just seen. What this means is that on our first call, we're going to get a coroutine frame. It's a heap allocated object that's going to hold our local variables, our arguments, and most importantly of all, the suspend point, where we're going to actually resume from when this gets called again. And in turn, we get a coroutine handle in the place where this is being called from. And that coroutine handle, it's just a pointer to that coroutine frame. And so once we've gone and moved on, that coroutine frame is going to go and live on, even when the coroutine is suspended. And this is where tasks, promise types, awaitables, all of these things come in. I'm not going to go into any of the code of them here, but Dietmar Kuhl, he gave a great talk at ACCU 1 year again on implementing the promise type, and I highly recommend that for understanding the machinery here. Our coroutine frame itself, it's just really going to hold some value, which is then going to tell us where to resume the coroutine from when it's resumed. That's the whole state machine part of this, if you've ever heard that in reference to coroutines. And this means that when we are going and suspending, when we're going and moving from one coroutine to another or elsewhere, we don't need to go and save CPU registers, kernel stacks, or deal with switching threads like we were before. We're just storing the current instruction position, returning control to the caller. And resuming is equally cheap. We're just jumping back into the frame itself. It's all comparable to just calling a function. Vastly cheaper than having to deal with the threads and the context switching. And it's all up to us when we go and run our coroutine as well. It's not something that we have to wait for the scheduler to go and decide when it runs. It's up to us. And just to try and draw a parallel to what we had before, the scheduler in the kernel was going and being responsible for taking our threads through these states of running to blocked, then back to runnable again. Our coroutines, we're sort of doing a little bit of this ourselves. It's us doing it in our application. As we're going from running our coroutine to suspending it, and then marking it as resumable at some point. I'm going to be adding it back onto a queue. And so if we go back to our event loop from earlier, this is roughly what it might look like in the actual calling code itself. We have our event loop in main, and we're just posting some work, which ends up in the queue inside of it. Well, this is how we can just simply schedule coroutines as well. So if we start at main, we've now got something which is calling our coroutine function, and it's taking a reference to the loop itself. Inside our coroutine function, we're going to co-await something that's awaitable, and that's going to suspend the coroutine. In the meantime, the event loop is going to keep on running. And we have this awaitable thing here, which is it's going to tell us what to do when our coroutine is ready to resume. And so in this case, where it's taking a reference to the loop, this is suggesting that, okay, when it's ready to resume, it's going to be put back onto the queue in that event loop. Now, not all coroutines, they don't need to be expressed this way. This is just like an example for illustration in terms of how to schedule them. Like in practice, libraries like CPP, Coro, Folly, ASIO, they are kind of doing this for us. They've got their own waitable types, and they're all just schedulers. Like that's all they're really doing. They're just an example of having gone and moved that scheduling from the kernel up into our application. And so this is combining the non-blocking scalability of event loops while still having the straight line readability of threads. But what's wrong with this? I shouldn't have left a co-await on this slide, but we've already seen that for our event loops to run successfully, that we need to have non-blocking API calls, where we dispatch some work and eventually we get a result. And that's exactly the same execution model we need here in a coroutine as well. Like remember, one of the things we have lost from moving from the scheduler and moving that into our application is the fairness aspect, in which previously it would be the scheduler would go and context switch jobs off of the CPU to make sure that each thread had time to run. Now that we're scheduling this in our own application, there's nothing to do that for us. Like we have to make sure that we're all playing nice, that all of our participants, all of our tasks are going to be being fair as well. They're not going to block the event loop. There's no preemption. Nothing's going to stop them from just continually running. And so what this also means is that the type of work we're trying to do is going to matter. If it's something that's going to execute without yielding and take a very long time to run, then it's just going to hold up other work. That blocking call for our coroutine, if it was something that was CPU heavy and running for a long time, it would just block tasks. And we can generally categorize the types of work into two things. We've got IO-bound work and CPU-bound work. And so for our IO-bound work, this is all where our bottleneck is just waiting for data from outside the CPU itself. If an application was just doing everything serially, just one after another, then the amount of time just spent waiting would be cumulatively adding up. While one message is being processed, our application would just be sitting there not doing anything, be waiting for a response. And meanwhile, other applications would just be stuck behind this one, waiting in a queue before even being run. But with non-blocking I/O, we're thinking about how can we make better use of that time we spent waiting. And that's where coroutines and non-blocking are a perfect fit. Like the CPU itself, it's not doing much work at all. It's just stalled. And so, for example, this could be reading and writing to a socket. That example we saw earlier that was blocking. Could be waiting for a database query to complete, or it could be calling a remote API over the network. Any of these things that just rely on our application doing a lot of waiting. And coroutines really excel here, as they can just co-await the I/O application operation and instantly and cheaply suspend until data is ready without wasting CPU cycles. And so we can go back and compare that to our threads from before. We've still got logical concurrency on the x-axis here and the throughput essentially on the y-axis. Whereas threads had the inflection point and started losing performance relatively early on compared to this, coroutines just are far and away outpacing them. But notice there's a very interesting caveat here. We mentioned that threads work well up to a certain point at which the overhead becomes too much and we oversubscribe the CPU. Well, look how for a sufficiently small amount of logical tasks, the performance between threads and coroutines is actually remarkably similar. The throughput increases at the same rate, and I've intentionally not put any values on the x-axis since I don't really want to open a Pandora's box as to, well, what value is the inflection point and what should I be using when. But it's going to depend on like your own machine and how much else is going on. It's generally going to be in the hundreds, if not low thousands. And at some point, there is going to be that switch from where threads work best to where coroutines are. And that's because we took all of that expensive stuff that the kernel was doing, and we're now doing that ourselves. It does mean that there is going to be an inflection point for coroutines at some point. It's just now that inflection point for coroutines is so far away because it's so cheap to go and have a context switch in coroutines. And I should point out in this graph, these coroutines, this is just a single threaded event loop as well. There's only one thread here. But we could also contrast this to if we were to try and do CPU-bound work with our coroutines. Really, there's not much difference between threads and coroutines on this. We're not going to gain much performance at all. Like there's not really an advantage to going and using them here at all. And in some cases, I think the performance would actually end up being worse. And so that's where, with CPU-bound work, we're still going to need threads, thread pools. And the bottleneck is just going to involve computation. We're going to have a threads getting dedicated time on the CPU just to keep crunching through data and run. And so this could be things like working with large memory data sets or parsing or compressing a large file. But in practice, probably end up with applications that have a little bit of both. We might have coroutines which are going and doing some I/O operations. And then at some point, we might go and hand that off to the thread pool. So we might end up something like this. We'll be co-awaiting on some I/O. Then we might take the data from that, the result we get, and go and schedule that on a CPU, perhaps. At that point, when we get a result from that, we can go back to doing I/O again. We can chain things together in this way. And that's why I wanted to also mention C++26 and std execution here as well. This isn't the talk to go into details about std exec itself, but it's one of the things we get from it. Because our applications, we do have a mixture of threads and coroutines, and we need to express where we want to schedule work and how we want to schedule work. It lets us compose I/O-bound work and CPU-bound steps in one pipeline, making explicit where each piece of work actually belongs. And because coroutines themselves, they don't know where to resume. The executors from std exec, they're letting us say, when I'm ready, resume me on the right resource. That's how we can avoid accidentally ending up doing CPU work on our event loop thread or spinning up the thread just to wait for I/O. And so to sum up, threads, they're great when, they're great for CPU-bound work. Right? The OS is going and deciding which threads to go and run on which CPU. They're a necessity for parallelism. We're going to get parallelism up to the number of cores we have. And then beyond that, the scheduler is going to start introducing context switching, and we're going to start getting some concurrency from that. The result of that is that they just don't scale, and they're expensive. And so that's where we start to see more advantage from our coroutines and from using coroutines. Because we've taken responsibility for that scheduling, brought it back into user space, but we've had to make sure that everyone's playing fairly. All of that complexity that the scheduler was doing for us and all those responsibilities it was doing, we've got to be going and implementing that ourselves. And that's where it's all cooperative scheduling. Like we need to be the ones making sure that tasks are yielding. And ultimately, the glue to go and put that together on the coroutine side is where we have our executors and schedulers, like our event loop and more complex patterns as well. And that's everything I had. Final things on here. Bloomberg is hiring. My team itself is hiring as well. That's the second link there. I'm also very proud at Bloomberg to be part of our internal C++ community. It's a fantastic place to be with some fantastic people from all corners of the company. And we recently published an article on our blog as well, discussing that community. So feel free to go and take a look at that as well. Yeah, thank you. Any questions?
You talked about cooperative scheduling and how you have to make sure the code kind of is well behaved in that context. Do you have some examples from your work where you inadvertently wrote code that was ill behaved and that caused starvation for that?
Some of the examples that I found often come from when we've tried to give something too much responsibility. So a function might have started off small and it might have had a very specific purpose and what it was trying to do. Over time, as the needs of the application has evolved and it's just doing more, it's more complex, things start to creep into that function a little bit more. It start trying to do more in that place just through convenience. That's where data is, perhaps. That's where things need to run. And so it tends to be that sort of scenario where I see in practice where something that was originally well behaved has over time slowly degraded as more and more has been added to it. And it's one of those things that occasionally have to keep in check and make sure that we're maintaining good quality code and everything.
Is there a static way to check for that? Or is it like you test and see what happens?
There's not a static way because all of this is going to be runtime. It could depend on the sort of abstractions you've got in your code itself, though. I think if you've got very clear abstractions and delineations in your code as to where you actually are scheduling some sort of CPU-bound work to any like I/O things, or you're making all of your code go through a standard I/O handler or something, and the same for CPU work, then maybe you can get something which will go and actually statically check. But for the most part, I think it just takes discipline.
Just so I make sure I understand it. So you had with your thread-based work, it was essentially constructing a new thread, a thread to just do some work, and then when it was done,
Right.
Keep them sort of running forever.
So for that example, I think that was still going and just creating threads and leaving them run forever. Well, not necessarily forever, but until their work was actually done. And it's just a fact that at a certain point, once we keep adding threads, because each one needs to go and get time running on the CPU, it's going to take longer for that piece of work to actually execute. So the thread's lifetime is just going to get longer and longer as it has to wait for everything else first.
And with the coroutines, that was essentially you had your single thread, main thread, if you will, and you were just constructing more and more coroutines, just like make a bunch and just run the same sort of work.
Absolutely, yeah. They're so cheap to go and create. The same cost as like a function call, so that's where we get so much more scalability from our coroutines. Cheap to create, very fast. We don't have to pay that overhead cost as well. At some point, we will start to see an inflection point like we did at the threads, but it's just so far out there that couldn't fit up in the same graph.
Thank you, great talk. For switching between coroutines and threads and the same workflow, how big of an impact does caching validation and other memory usage issues performance, specifically because you are sandwiched between two talks about that subject?
It's a great point. Definitely go to Michelle's talk after this to learn more about caching. This is one of the things. Like as we are going and running jobs on one on one core, any data that we need is going to be pulled into the caches specifically for that core. But if we're going and, well, firstly, if we're then going to go and like block on that thread, we could end up running on a separate core afterwards where we're just not going to be anywhere near that cache. But also in place of that original thread, for example, there's going to be a new thread running, even if we're just going and preempting. And at that point, there's going to be some cache thrashing as well, because we're going to be then pulling in the data we need for that thread. And so you can work around that with being able to go and, for example, pin threads to certain cores, or at least make a strong suggestion that, okay, this thread should always be executed on this core. And you can use your thread pool to go and get a very long way with that. With coroutines, because we're generally going and multiplexing a huge amount of these onto a smaller number of threads, you're less likely to go into the case of like a coroutine and that thread being on a different CPU, still entirely possible. But I guess if you're trying to go and pin it to a certain CPU generally. But we're going to have so many of them that we're going to be, your caching performance isn't going to be like the same. It's going to be going and just having a huge amount of data going in and out at any point in time as well.
Great talk, thank you. Just wondered, are there any standard library features that would help you make coroutines more usable or improve interoperability with stood execution? DeepMar has its task proposal that hopefully we'll get into 26. Can you think of any other examples?
That is the main thing that is going to get us there for it being more all as part of the standard itself, like stood execution, the things that tasks coming in C++26. Before then, we've got libraries like CppCon, Folly, ASIO, and like Boost Cobalt are great as well. They can do a lot of that for us. Like at a certain point, like we need these types, but we also need the scheduler itself. And so these libraries are going providing both the types, the tasks, the promise types, and everything, and then also all of the schedulers, like the glue, to go and be able to go and say, okay, where should this be running, and where should it be resumed, and so on.
Thank you.
Thanks a lot for the talk. You mentioned that coroutines are stackless and that the coroutine framing is heap allocated, but also that coroutines are very cheap to create. Do you also have to consider the cost of that memory allocation in spawning a coroutine versus just a regular flow?
Yeah, it's a good point. It's a very small heap allocation. So in practice, it's not a huge amount of overhead to it. And there are ways to go and try and optimize that a little bit more. So already going and having a dedicated section of memory, which you can go and pull from for that. There are ways in which it can be elided as well. I think it's sufficiently niche and rare that it can be elided that off the top of my head, I can't remember the exact criteria for it. But at a certain point, and the same with like threads as well, like memory is going to come into it. I think with threads where it's like each stack is what, like a megabyte or something. With coroutines, they're going to be so much cheaper because that frame just needs to hold a few pieces of data, just like where we're going to resume from and any local variables that need to be kept alive throughout pausing, suspending our coroutine, and then when it's resumed again afterwards.
Thank you.
Thanks for the talk. So if we follow like the presentation as like a progress line, so we first have like one thread, see all the work, which is slow, so we want to increase throughput. So we throw more threads at the problem, we'll increase it, and then afterwards it slowly gets worse. And then we pull back on the threads and then throw coroutines at the problem with a single thread, and we get that much better scalability.
Yeah.
So I was asked, so if we, assuming all the IO APIs we use are non-blocking, is there still value in having, the build off of that's a single thread?
Yes.
Is there still value in having multiple threads? Maybe not like 1 minute.
Sure. Yeah. No, it's a great question. Yes, we will still start to see some increased performance if we have our coroutines running on their own pool with however many threads as well. It's not exactly going to go and like double this, so it's not going to be exactly twice the size of a list line with twice the throughput. I think I did have a graph on here in this talk at some point where I was going up to a thread pool of size 8. I think I deleted it, so I don't even have it if I go back and exit the slideshow to see if it's still there. But yeah, there's definitely possible as well. It's not going to give you huge improvements in your actual throughput itself. And I think for the most part, a single thread will get you an incredibly long way before you start needing to actually deal with that. But if you find that your application is going to go and need that, then by all means.
Also talking about this graph, I'm curious, like, what was actually running in these coroutines? Like, what is being tested here?
So in these coroutines itself, I was going and making some call, which was then going and yielding, and then going and having another call coming in, going and trying to do some work, which would then go and yield again. So these coroutines themselves, they're just constantly going and kicking off something, kicking off some work, and then yielding, going back to our event loop, letting it pick the next event, and then eventually at a certain point when that data is ready or that event is ready, they're going to come back and continue again.
Okay, so were they actually like blocking or anything? Or I guess no, they wouldn't be blocking, that's the whole point.
Right.
Thank you.
All good.
Great talk, thank you. What are the implications of coroutines being stackless? Do we not get access if we end up popping up in the stack and then resuming? Do we lose access to data that was on the stack?
It's not necessarily about losing data that was on the stack itself. If there was anything that the coroutine frame itself needed to continue execution, then the compiler would already make sure that that is saved within that coroutine frame itself. There are implications in terms of everything from like memory usage. It's coming with its own stack. It's going to be more expensive. I'm going to tentatively say that I think performance is still generally pretty similar in terms of what you'll actually see. It's been a while since I've gone and probably benchmarked the two in comparison. But yeah.
Cool, thank you. One more question. Are mechanics exposed at all, so potentially we wanted to provide additional information onto that frame? Is there ability to do that, or is that?
So this is one of the big things with C++20 coroutines, and I think one of the reasons why there's been so many talks on just here's how to write a promise type and everything. It's because they're so customizable. That's, I think, where a lot of the complexity and sort of like intimidation factor of them comes from. Just the fact that there's so much you can do to customize how they behave. And at the moment with pre-C++26, it's stuff that we have to implement ourselves.
Thank you.
Thanks for the talk. Between the points of divergence between the two graphs and the inflection point for the threads, it's almost like a step function. So you add one item of concurrency and then the throughput jumps significantly. Why is that?
What are you referring to, sir?
So the graphs, so at first they coincide.
Yeah.
And then there's a point of inflection for the threads, right?
Yes.
So if you look at the graph, the red graph, between these 2 points, it's almost like a step function, which means that you essentially add one item of concurrency, and the throughput jumps significantly. And I'm just wondering why is that?
In the case of like the actual rate at which it's increasing.
Yeah, you can see that, okay, they're not exactly horizontal. Right?
Yeah.
But you look like a step function. And so there's some discontinuity between probably what is like, n to n plus 1 concurrency, and then you can see a jump in the throughput.
Yeah.
I'm wondering how that can happen. I can understand, the inflection point, and I can understand that the 2 points are probably some noise, but it seems relatively consistent, at least with the
So that could be things like, earlier there was mention of caches as well. This could be just a little bit of noise in the data generally. I think it'd be hard to necessarily read too much into specifically what is causing that pattern. I think it's just going to be the fact that yeah, there's all of these other factors at the same time as well. Like the preemption and context switching is part of it, but whatever else is going on is also going to play into it and add to those costs as well, like caching or anything else.
Hey, good talk. I'm just curious who's providing the non-blocking IO functions. Are you implementing them or is it standard library?
So, great question. You can implement them yourselves, but you probably don't want to. You probably want to have some library or something which is going and actually wrapping them. There's a few functions that the actual kernel exposes, called select, poll, and epoll, which are all ways of going and registering interest, our application registering interest on a set of file descriptors, set of resources, and then us going away and doing our own thing. And then the kernel itself, when something is ready for those file descriptors, will come back and let us know. And generally, there are going to be libraries which will go and take care of all of that for us. They're going to be implemented in some one of these. It's not something you should really want to write yourself. I think with all of this, like the more abstractions in our code, the nicer it's going to be to work with. But those are the underlying mechanics of it. And I think I referenced here my teammate Philip. He gave a talk on this a few years ago. It's on YouTube. And I think it's called What I Learned from Unix Sockets. And the premise of that talk is all about the concept of readiness and what it means for these to actually be non-blocking all of a sudden. Cool. I think that's it. Thank you very much.